Perfect. Yeah, so we're live now. Let me skip back to our first slide. Awesome. So hello, everyone, and welcome to our Foundation Exam Study Jam and Info session. So my name is Hannah Moss, and I am the Google Developer Student Club at UCF lead for the upcoming year. And I'm super excited to tell everyone a bit about our club and ways to get involved, and then jump into an FE study session. In our FE study session, we'll focus on the 5 most commonly missed types of problems, give you some tips and hands-on practice, and play a Kahoot. So let's jump in, and I'd welcome speakers for the day. So our speakers today are Camila, Ryan, Nikhil, me, Hannah Moss, and Harrison. However, we had even more awesome support from the current core team members who are not speaking today, who helped make this event exactly what it is going to be. So check out the About section on our webpage, dcsucf.com, to read more about each of them. And as we go through the event today, keep posting those awesome comments, because with any questions you have, and we love the involvement we're seeing so far. Yeah, so first, before we move forward into our FE study session, I want to give a quick overview of what the Google Developer Student Clubs are actually about. So Google Developer Student Clubs, or GDSCs, are student-run communities supported and recognized by Google developers. Google also supports developers through similar programs like Google Developer Groups and Women Tech Makers. So the objective for GDSCs is to help students bridge the gap between theory and practice. But what does that actually mean? So in our classes, we learn a lot about theory or concepts, but oftentimes we don't get the chance to apply these to real-world problems. So that's what our club is here for. So through your participation in our events, you'll learn about cutting-edge technologies and platforms that you can use in real-world applications. And we really want to help you through peer-to-peer learning. Remember, it's a student-run community, and we want you to reach out and ask any questions and ask for help if you get stuck. This way, we can meet new people and build projects together. That's our main goal in our club, and we hope you enjoy today's event. And if you like today's event, we have plenty more coming, and would love for you to get more involved with our club. To join, all you have to do is join our Discord server. It's free and easy to join. All UCF students, regardless of major or field of study, are welcome. To join, please visit dcsucf.com/go/discord. And the link is also on our main page of our website, dcsucf.com. Cool. And if you're interested in becoming part of our leadership team, known as our core team, we are now accepting applications until August 30th. So if you visit our main website, dcsucf.com, again, you can see the core team roles and a link to the application. And I will have, my team is eventually going to drop a link to our site in the chat and in Discord. So Alice, if you can drop a link to the DCS UCF site in the comments, that would be great. And next, let's jump into our foundation exam study jam. And so first, I wanted to go over some tips and tricks for foundation exam success. And these focus both on what you can do before the exam, really exam day, both in the morning and then when you're actually taking the exam. And so first, before the exam, so every time you study, it's really important to replicate the exam as much as you can. And that can mean trying to take it on paper, trying to make sure you're sticking with the same time limits that you'll see in the exam, and just replicating it every way so that when you actually get into taking the exam, you're ready, you don't get hit with any things that you weren't expecting. Next thing is, and this you'll hear this everywhere about the foundation exam, but it's to study previous exams. These really can give you the best idea of what you can expect on your exam. And one thing to keep in mind when you're studying past exams, so you can kind of see the patterns of what material might appear on your exam, but make sure to study things outside of that pattern, because a lot of times they switch that up, and you want to be ready for anything. And next thing that you should do when you're studying for the foundation exam is note down trouble areas. So when you're going through problems, if you have, you're going through a problem and you're like, oh, I really don't know how to do this, note it down and keep noting down those patterns so that every time you have trouble in an area, you get like a list of, these are the areas that I struggle with the most, so that those are the things you can focus on the most when you're studying and you can see your improvement there. And the last thing is really just sticking with it. The biggest thing is practicing as much as you can, and really just going at it again and again so you're really prepared. And then actual exam day, so make sure to get some rest the night before and eat a good breakfast. It can be really easy to convince yourself that an all-nighter is the best option, but you need your brain to be working at optimal peak performance the next day. Um, and the next item is, so when you're actually in the exam, and this is something that I did on my exam. So when you immediately get into there, get the sheet or the web courses link up in front of you. So you're going to jot down any memorized info at the beginning. This is to make sure you don't, like, it doesn't slip your mind as you're going through problem solving and the other steps, and it's just there for you. And the next step is to look over the entire section that you have before you start working on it. This helps you get kind of an idea of how you want to manage your time through the exam, um, and really just helps you like complete it in time and all those items. The next thing is to move on from a problem when you get stuck. And this is kind of unlike the stick with it before the exam, because before the exam, if you get stuck on a problem, you should power through it, keep working on it. But in the exam, you have really strict time constraints. So if you get really stuck on something, just move on, let your brain process through it in the background, and come back to it when you have time. And then the next item is don't leave anything blank. So this is a big pointer, because even if you don't fully understand a problem, writing down your mental process and what you're thinking about, and maybe a solution that you're not so sure about, can mean that you get like some points where you would get none if you wrote down nothing. And then if you are at the end of the exam and you have um, some extra time, so what you want to do is make sure you double check everything. Use that time to your benefit. And those are some main tips and tricks for the foundation exam success. And the next thing we're going to do is move on to a Kahoot. And 1 second, I want to verify if I'm going to be screen sharing this Kahoot or not. Uh, Getting a message. I'll just pull it up for now. Okay. So we have our Kahoot here, and make sure you're playing along, join in as we do this Kahoot. Sorry for a second. I'm gonna log in. Okay. Yeah. Always have a little bit of technical mix-ups when you're planning an event. So I am going to sign up right now as Kahoot. And I'm going to do this on a separate screen. Just taking 1 second. So while I'm doing this, feel free to drop in the chat any questions or comments that my team can help us with. Okay. Yeah, and thank you for, I also love the Totoro Chrome theme, just so thank you for pointing that out. Cool. Okay, so now we're going to play this Kahoot, which was created by one of my awesome core team members right now. And we're going to do classic mode and get ready to join, everyone. So pull up Kahoot on your side. And hopefully we can hear the Kahoot music in the background. I'll give a few minutes for everyone to join. Yeah, and my team, feel free to join if you want to, even though we already played this through. Always good to get some more practice. And I'll probably wait till like 1:15, give about 4, maybe more minutes, depending on how many more people we see joining. So the joining seems to be slowing down a little bit, so I'll get started at about a minute. Get ready to test your FE knowledge with this Kahoot. So like 30 more seconds, so make sure to join if you want to play, and then we'll get started. I'm enjoying the names. Hello, Crouton. Cool, okay. So it's 1:13, so I'm gonna get started with our Kahoot. Yeah. So what is the post-order traversal of this tree? Make sure. Let me. Yeah, and so most of these questions have kind of a short time limit. So even if you're not super sure, just pop something in there. And let's go to the next one. So far on the leaderboard, we have Jackie, Crouton, and Talkit. Cool. So what are the worst and best runtimes for a try search? Okay, one person got, and this also helps because you can look at, this is something I need to study in the future. Sante on the board. We still have Crouton, Jackie, and Talkit. Let's go to the next one. True or false? The worst case runtimes for a BST search, insertion, and deletion are all O of N. Awesome, 23 answers on this one. Ooh, good job, everyone. Crouton in the lead. Okay, true or false? The worst case runtimes for AVL tree search, insertion, and deletion are all O of N. And I hear there's some lag, so that's rough. Awesome. Most everyone got that right. Ooh, Batty is the highest climber. Okay, next question. What kind of data structure are stacks? So are they first in, first out, or last in, first out? Yeah, and this is something you'll definitely want to know for the foundation exam. Cool, okay. Crouton still in the lead. So in an empty hash table of size 7, which index would an element with hash value of 3 be inserted at? Just pop an answer in if you're not sure, because there's a time limit. Cool, we got 10 with right answer, so good job. And apparently it was a tough question, so let's go to the next one. So what does malloc fill in with each block after being initialized? Gotta have the memes, of course, for the Kahoot. Yeah, garbage value. Awesome job. Okay, next one. So what tree traversal uses the following pattern: left, right, and then root? Yeah, so the correct answer for a left-right root tree traversal is post order. Son as the highest climber, up 6 places. Good job. Okay. This is a multiple select, so select any that apply. Which values of the following min heap remain unchanged in position after 14 is deleted? We have 30 seconds on this one because it's a little bit of a tougher one. And remember, this is multiple select, so select all that apply rather than just one. And another pretty tough one. But so 40, 72, and 80 all stay in the same position. Cool. And we're on question 10 of 15. And what is the result of this bitwise operation? So we're doing a bitwise OR here. Fortunately, the answers are also in binary, so that helps a little bit. Good job, all 9 of you, and everyone else who is joining. Ice with the highest answer streak of 4 is up to number 1. Okay, what is the pattern for in-order tree traversals? And remember, we had an answer about left-right root being another post order, so just a little hint there. Awesome. Okay. True or false? Calc has 2 parameters or arguments compared to Malik's 1. Awesome. Okay. Next. We have 2 questions or 3 questions left. What is the pattern for pre-order tree traversals? So we've gone over all 3 types: pre-order, post-over order, and in order. So. Yeah, root left right is pre-order tree traversals. Okay. Last 2 questions. The cue is last in, first out data structure. So this in stack is definitely something to look into. Remember that queue is first in, first out, and stack is last in, first out. So true or false, the runtimes for bubble sort are best O of n average O of n squared and worst O of n squared. Well, yeah. And this is our last question. So make sure to answer correctly and quickly. Awesome. Okay. Let's see who won, who's on our podium. So we have Talk It in third place. In second place, we have Batty. And in first place, drum roll please, We have ice. Congratulations, you guys. Awesome job showing your knowledge for the foundation exam. Let me close out of this. And we're going to continue on with our studying for the foundation exam. So now that we're done with the Kahoot, we are going to go into our problem type overviews and talk about the 5 most commonly missed types. And first up is summations. And Camila is going to be talking about summations.
Hi everyone, so my name is Camilla, and today I'm going to be going over summations, which is one of the 5 most missed problems for the foundation exam. So first we're going to be going over the tips and tricks. So the first tip I have for you guys is just to practice. Practicing is really important for summations because it's the best way you're going to get at understanding these problems, and you're actually going to start seeing some patterns within the summations that once you start practicing enough, you're going to be able to assimilate these problems and be able to remember them from before, and it's going to be much easier for you to do these problems. So secondly, breaking down the summations is also really important. It makes it much easier for you to be able to clearly visualize the problem and see it more. It becomes easier in that way, and you're also going to be able to plug in the summations formulas really easily if you break them down. And then lastly, memorizing these summation formulas, which are on that slide. That's really important. You're going to need these for basically every single problem you do for summations. These are very, very important for you to memorize. So what are summations? So for the foundation exam, you're generally asked to find the closed form of the summation. So here in this picture, we can see the general form on the left side, and you're going to be asked to give the closed form, which is the one on the right. So we're going to work from the left side until we have the right side. So how do we approach this type of problem? So the first thing we're going to want to do is to play around with the form until we can see that we can use those summation formulas and we can plug those in. So this could look like factoring, for example, or pulling out some constants. And then another thing we have to do until we can plug in the summation formulas is breaking that summation if we can. It's really makes it much easier. So those are things that we have to do before we can actually apply those summation formulas. And after we apply the summation formulas, we just basically simplify our answer until we have the clean closed form that we want. So let's try one together. So if we're given this closed or general form and we're being asked to find the closed form of this. So the first thing we would do here is try to get it more simple so we can um, break down our summation. So here we can see that we have factored out that function, and now we can clearly see that we can separate this into 3 clear summations. So next we're going to separate that into 3 summations. So now we have our 3 summations. So here next we can actually see that we can plug in our summation formulas. And here we have all of the summation formulas that were used for this problem. And also, guys, if you have any questions, please put them in the YouTube comments. I'm going to try my best to answer those, or our team can also answer. But here are summation formulas. So for the first part here, we have k squared, which we can easily use I squared for. So we just basically plug that one in. Then the second formula we have is actually a constant before the function, and we can just take out the constant and we can put it at the beginning of the summation, which will just basically be multiplied over the entire function. So here we can see that we pulled out that 6 in front of the k. and then we can continue with the other summation formula just for k. And then lastly, we have our just another constant that we just multiply by n. So we have 9n for that. Next slide. So at the end, we just basically simplify everything and combine like terms until we have a pretty clear, clean, close form of that. Next slide. So now it's your turn. If you guys want to try to work this one out. So we're asked to, it's the same thing basically. We're asked to give the close formula for this summation. So a good hint for this one is that for the formula that just has the one n, we can actually substitute that for n over n to the power of whatever. So we can use that for n to the power of 4 for this example. So remember to use those summation formulas that were displayed at the beginning. And then I'm going to give you guys about 10 minutes to work these out. And if you guys are done with the problem, we're also going to be displaying hangman on the side. So when you guys are done, you can play as well. And then I'm going to be going over the answer. Okay, everyone. So it's been about 10 minutes. I hope you guys were able to work out this problem. I saw a lot of people are playing hangman, so that's good. So let's go over the answer for this one. So here the first thing we're going to want to do is pull out the 6, which is a constant. We can pull it out so it's easier for us to plug in the other formula, which is just the formula for I, the summation formula for I. And instead of using n here, we can use n to the power of 4, which is basically just the same thing. And then after pulling out the 6 and plugging in that formula, we can just solve everything out. And then at the bottom here, we can see basically the breakdown for the grading. And this is from a foundation exam from a previous year. So we can really see what the teacher is looking for these answers. So I hope you guys were able to practice a little bit and figure this problem out. And if you guys have any questions still, you can comment on YouTube. But the next problem we're going to be going over is recurrence relations, and Ryan is going to be going over that.
Hello, everyone. I'll be discussing in particular recurrence relations and how they are normally done in the foundation exam, and moreover, how I like to do recurrence relations. Recurrence relations are these type of mathematical problems that involve determining the runtime for a recursive function. Let's go over a couple of tips and tricks that I like to utilize when I work with recurrence relations in particular. First, I like to keep track of the initial function t of n. Every time you're going to be given a recurrence relation problem, you're usually going to be given a t of n, which represents the recurrence relation, and a base case. When we're going through this presentation today, I will be using some terms such as base t of n, which simply refers to the t of n or recurrence relation that you're given in the very beginning in the problem statement. The second tip I have is to set up a table to keep track of your work. If any of you folks have never worked with recurrence relations before, or if you have worked with it, you ought to know that they're a very messy type of problem. You're going to have multiple steps, a lot of simplification, and really, really long functions. So the best way that I like to do in order to keep track of my work is to represent my work in this table in this screenshot below. This is just an example pulled from a YouTube video in which several other people also employ this method. If you ever are doing a foundation exam, a mock one, and look through the answer, you will see Guha, the person who is responsible for writing the foundation exam, doesn't utilize this format. But this is a totally acceptable format on the foundation exam, and you will get just as many points as if you did it this method or Guha's method. Next slide. Another tip I have is to simplify your work at each iteration and keep track of the unsimplified work. What I'm referring to this is if you look at the screenshot here and look at iteration 3, or where it says k equals 3 and the thing to the right of that, you'll see that the simplification is on 2 levels. And the reason why I like to do this in particular is because I'm able to look back at things that I've simplified too far and see what the, I guess, actual recurrence relation should be at the end of the day. The point of near the end of your recurrence relation problem, you're going to have to find a pattern. And if you simplified your work too far, you would realize that the pattern isn't easy to see. However, if you're able to look back at the parts that you simplified too far, the pattern may come to light more easily. And the last but certainly not least tip is to practice. As with most mathematical-based questions and concepts in the foundation exam, you should always practice in order to better your ability to see the patterns in these recurrence relations and more easily solve them on the foundation exam. Next slide. Now we're going to go over the common steps I like to utilize when it comes to resolving a recurrence relation problem. Now, once again, this is not the end-all be-all way to solve a recurrence relation problem, but this is just my way in order to make it more easy and approachable. First is to create a table, like I mentioned earlier, with k on the left and t of n on the right. K represents the steps, i.e. when I say k equals 1, I mean the first step of the recurrence relation. The second tip, the next step I like to utilize is to set up the first iteration, i.e. where k equals 1. For the first iteration, it's always going to be the base t of n given. In other words, the t of n that you're given when you are given the problem statement. The next step that I like to do is I like to fill out the rest of the table with the appropriate iterations. Now, I have a little technique in order to work with every iteration. If you looked at the previous slides and the previous screenshots, you'll see that as you go down the iterations, the problem gets larger and larger. And this gets pretty messy and hard to kind of follow through. So one of the ways I like to approach it is in this simple format. I like to delete t of n from the previous function. Whatever was the answer to the previous iteration, I just bring it down and delete t of n. Then what I do is in that empty space, I paste in the base t of n given in the problem. But as opposed to just inputting n from the base t of n, I input the new value of n. Then I simplify and repeat. Now, once hearing this, it may not make a lot of sense just speaking it to you, but we're going to go over a practice problem, so this makes a lot more sense. The next step I like to approach is to formalize our pattern. Once we are able to formalize our pattern, you might have summations arise, which you'll have to employ some summations techniques in order to bring the problem down to a closed form. The fifth step I have is to use the given base case. For every recurrence relations, what you're going to want to do is to want to get rid of the t of n, you want to get rid of the k's, and you want to put everything in terms of n. Indeed, if you're finding the runtime for a normal function, not a recursive one, you're usually going to be very accustomed to the n, the O of n's, the O of n squareds, etc. And just like those, a recursive function will also need to be represented in terms of n. And the last but certainly not least step is to simplify. Next slide. Now let's walk through a problem. The first step, like mentioned earlier, is to always create a table, k on the left and t of n on the right. Next slide. Then we're going to set up the first iteration. Let's work on this problem in particular. In this problem, we have t of n is equal to 3t, open parentheses, n minus 1 plus 1. And then we have a base case, if you look underneath that line, of t of 1 is equal to 1. Now for the first iteration, like I mentioned earlier, the first iteration is always going to be the base t of n. In other words, whatever is given in the problem statement. So it's very easy. Whatever I'm given is whatever I'm plopping down for the first iteration. Next slide. Now for the next iteration and onwards, this is where it gets a little bit harder. So if you're not following through, it's okay. These slides will be published by the DSC, and you can always look back at this in order to refresh your memory. But I'm going to make it as simple as possible. So we know the first iteration is 3t n minus 1 plus 1. If you look at what's in red, what I'm going to do is I'm going to delete the part that says t n minus 1. I represent this as just an empty line. But when I delete this and leave empty space, I want to remember what was inside the t of n before I deleted it. Inside the t of n, it's n minus 1. I want to remember that value of n minus 1. From there, what I'm going to do is paste in the base t of n, in other words, what's in the right-hand side, also what's given at the very beginning, into that empty space with the correct n value. Now, if you look at that empty space and put in the base t of n, you will see something close to what I have in blue underneath, except you will realize that I have an extra minus 1 there. Now, if this doesn't really make sense, look at what's on the top right on top of the table. That's the base t of n. And then look back at what's blue. The main difference is that I have an extra minus 1. This minus 1 comes from when I mentioned earlier to always remember what you deleted. I deleted t of n minus 1. This implies that for every instance of n, I'm going to replace it with n minus 1. That's why I have n minus 1 minus 1. From there in blue, I simplify it to down to n minus 2. And then if you look at the table on the right, I just plop it down for its respective k value, which is k equals 2. Next slide. Now from there, I'm going to simplify even further. So I'm going to do some easy distributions, distribute the 3 out, and then do some simple simplification, just add everything up, and I get a much nicer problem to see, 9t n minus 2 plus 4. But if you remember my tips from earlier, always remember the previous simplifications and always keep track of them. Next slide. Now we're going to do the same exact thing mentioned for the second iteration, but for the third iteration. So just to run it back one more time really quickly, if you look at the second iteration, The second iteration is 9t n minus 2 plus 4. I'm going to remove t n minus 2, put in the base case, which is 3t, my bad, not the base case, the base t of n, which is 3t n minus 1 plus 1. But remember, I'm going to swap n with n minus 2. So this gives me n minus 2 minus 1, which just gives me that n minus 3, which is what you see on the first line for k equals 3. And then once again, I'm going to do some distribution, some simplification to get k equals 3. Next slide. Now you realize here, I've only done it 3 times, but after these 3 times, I've done enough recurrence relations problem to see the pattern. This is why practicing is very important, because with more practice, you're able to see these patterns earlier on, and you're able to solve the problem faster. So now let's formalize our pattern. If you look at these 3 iterations, you'll see the constant on the outside is always increasing by the exponent of 3 base. In other words, 3 to the first power is 3, second power is 9, third power is 27, etc. And if you look at our table, the constant on the very left is increasing by that same pattern, 3, 9, 27. Now we want to represent this in terms of k. So this is why we set it up as a table. We can easily reference the k value in order to see the pattern more easily. Now k starts at 1. So I can easily represent this pattern as 3 to the k. Now what I want to do is represent the rest of the recurrence relation. Next to the constant on the very left, we have our t of n's. If you look at through all the iterations, we have t of n minus 1, t of n minus 2, and t of n minus 3. Now that's a very easy pattern. It's just 1, 2, 3. And so conveniently, it's also the way that our k starts. So we can easily represent this in terms of k by doing n minus k. Now, the last thing I have to do is I have to find a pattern for that value to the right of the t. We have a plus 1, we have a plus 4, and we have a plus 13. Now, you can be stuck on this all day and not see the pattern very easily, and that's kind of what I did too when I saw this problem. But if you actually look at the steps before we got those values, you can see a more easy pattern. You will see at k equals 1, we just have a 1. There's nothing we can do there. At k equals 2, we have 4, but how did we get that 4? We did 1 plus 3. At k equals 3, we have 13. How did we get that 14? We did 9 plus 3 plus 1. So I think we have a sequence. And from there, we want to formalize our pattern even further. We see that because we have a sequence, we can actually represent the last part of our pattern formalization in terms of a summation. So we set it up as a summation. 1, 3, 9 follows the pattern of the 3 exponent table. But as opposed to starting at 1, we start at 0. Indeed, 3 to the 0 is 1, 3 to the 1 is 3, 3 to the second power is 9, etc. So how do we represent this in terms of k? If we remember our table starts at k equals 1. So when we represent this, we don't want to do 3 to the power of k. We want to do 3 to the power of k minus 1. Next slide. So now theoretically we have our summation. Our summation is 3 to the power of k minus 1, but we're going to swap k with I, because that's how summations are usually written. 3 to the power of I minus 1, and we want to set up the bounds. Now the bounds for every recurrence relation problem is always I equals 1 to k. This makes sense, because we start our table at k equals 1, and then we keep doing these iterations until we figure out the pattern, i.e. we just have this arbitrary value k. So we have this summation. But I personally do not like that I minus 1 in the exponent. So if you look on the right-hand side, I'm going to try to get rid of the I minus 1, because I know my summation rules, and I know that I minus 1 is kind of hard to get rid of using purely summation rules. So I'm going to do some index shifting. Now, index shifting doesn't really fall within the realms of the CS curriculum, but Guha commonly uses it inside his foundation exam problems. So just a little, I guess, summation lesson here. In order to index shift, all you have to do is you have to get a new variable, set it to what you want your index to be shifted by. In this case, I want to get rid of the I minus 1 in the exponent in favor of just I. So what I do is I have another value, and I set it to just that. In this case, j. J is equal to I minus 1. Then I realize that at the bottom, the lower bound, as opposed to I equals 1, I want to do j is now I minus 1. So while I used to be 1, it's going to be now I equals 0. But since we're using it in terms of j, it's j equals 0. Now, this may be very confusing, but this is just index shifting. And if you need any more research on index shifting, I'm more than happy to give it to you near the end of this. But to just speed up past this, what I end up doing is I subtract 1 from the lower bound, I subtract 1 from the upper bound to get those values. And as opposed to using a j, I turn everything in terms of I because we like i's. And Guha usually doesn't change the variables when he's grading, when he shows the solutions for these problems. Why? I'm not sure, but I really like it when we switch variables because it's easy to see. Next slide. So now we have this new summation that's easy to look at. It's 3 to the power of I, but with a little bit weird bounds. I equals 0 to k minus 1. But we have our entire pattern formalized. Now what we want to do is we want to switch out every k in terms of n. Remember what I said in the very beginning. We want to turn everything in terms of n just like every other runtime problem. So what I'm going to do is I'm going to use the base case. The base case is t of 1 is equal to 1. What I'm going to do is I'm going to look at what's inside that t open parentheses. It's 1, or in other words, what's on the left-hand side. Even though the left and right-hand side both say 1, I want to keep close attention to what's on the left-hand side, which is 1. What then I'm going to do is I'm going to assign 1 to what's inside our t. So for our t in our equation, we have t open parentheses n minus k close parentheses. I assign that to 1, and then I use a little bit of simple algebra in order to figure out what k is. K is equal to n minus 1. So what I'm going to do is that for every reference of k, I'm going to swap it with n minus 1 so I can get my pattern in terms of n. And that's what's on the right-hand side. Next slide. Now, after doing a little bit of simplification, I get this. Now, t of 1, if you remember the base case, is equal to 1. So I can just cross that out because it doesn't really change anything. And now I have this problem. 3 to the power of n minus 1 plus the summation of 3 to the I with a lower bound of 0 and an upper bound of n minus 2. Now, a little quirky trick here that I used in order to get this into one summation is to simply look at the problems. I realize I have 3 to the I on the right, and I have 3 to the n minus 1 on the left. These can actually be put into one summation. 3 to the power of n minus 1 is simply the next iteration in the summation if I was to write it out by hand. Indeed, what comes after n minus 2 is n minus 1, and after n minus 1 is 0, etc. So what I can easily do is change the upper bound to be n minus 1 as opposed to n minus 2. If this doesn't make sense, all you have to do is just write out every iteration, and it will make a lot of sense in how this kind of upper bound changes. And we get this new, very easy to understand simplified summation. Next slide. From there, we have this easy summation. And using some of the summation rules mentioned earlier by Camilla, I'm able to figure out that the summation that I posted in the top right is a really nice formula in order to simplify this summation down to some easy numbers. And with that, I get a final answer of 3 to the n minus 1 all over 2. And that's kind of it. That's kind of how you resolve a recurrence relation. So now it's your turn. There's going to be a practice problem here shown on screen. And if you're done early or you wish to not participate, you can play hangman with us and vote for the letter of choice in the comments, as we'll be monitoring that throughout. Good job, guys, on getting the hangman answer. We're going to go over the problem now. So this is actually a problem straight from one of the previous foundation exams. And as you look at the solution, you'll realize that this is kind of how Guha likes to write out his recurrence relations problem. But if any of y'all did this problem, you would realize that it's a lot similar to the practice problem that I did, but a lot easier. There's no summations in this ones, and the patterns are very easy to formalize. However, a very big distinction between this problem versus the practice problem I did, which was kind of talked about in chat, was that the base case in this problem was actually t of 0 is equal to 1. And in that case, what we want to do is we want to assign our t of n minus k, in this instance, to 0 and not 1. And this is a very important detail that a lot of people mess up on and actually mess up the end recurrence relation. And that's kind of it for this problem. I'm going to be passing on the slides now to Nikhil, who will be talking about backtracking.
All right, hello everyone. My name is Nikhil, and I'll be going over the backtracking problem type in our problem type overview. So normally people confuse backtracking and recursion because of the similarities of the two approaches. The thing to note though would be that recursion is a way to solve a problem, and backtracking is an application of recursion in solving a problem involving many possibilities. So an example of this would be finding your way out of a maze. So you have different junctions where you have to make multiple decisions and multiple possibilities to explore. Backtracking tells you to recursively explore these paths by making choices at junctions until you reach the end of the maze. So yeah, make sure to practice problems like this conceptually to understand how the backtracking approach works and for which kinds of problems it works with. So some examples of like common backtracker problems include Sudoku and Queens and like other sorts of puzzle type problems. Next slide. So how would you approach a backtracking problem? First, you want to define your domain. So the domain would be the items you'd be continually looping over or your set of options in a given problem. Next, you want to identify your constraints. So your constraints of a problem are what allow your decisions to be valid. Some constraints can further break down into further subproblems or secondary constraints. Then you would want to identify the goals of your problem. Goals should be determined based on what success or failure looks like for a subproblem. You need to establish what needs to be done when a decision is made from the subproblem or whether it fails or succeeds, such as when a maze path hits a dead end or reaches an exit, or when you can no longer break down subproblems from their main problem. And finally, the last step is to actually construct the solution. So to do this, you want to think about what the goal of your problem is and return accordingly. Next slide. So here we have a common backtracking problem. So this is the n queens problem. In our example, we're going to use n equals 8. So in chess, a queen is an object that can move in however many spots in any direction, so vertically, horizontally, and diagonally. We want to place 8 queens on a chessboard of 8 by 8 spots, such that none of the queens attack each other, which also further implies that none of them can be placed on the same row, column, or diagonal path. And so now you can go to the visualizer. So as you can see through the visualizer, the way backtracking operates in this problem is by placing a queen down in a given row by column spot on the board and working out where to place the next queen so that it can't attack any previously placed queens. You want to try all the spots for each queen, and if there are no options to place this queen without conflicts, we want to revert back to the previous queen and try that queen in another spot to see if we have more options for our next queen. Sometimes even reverting back to a previous queen won't help, so we may have to revert back to queens even further behind. In this case, if there are nested conflicts, we want to try the same approach, but just backtrack to the appropriate queen, or we can try another placement. Next slide. So let's start with step 1. With this problem of placing 8 queens on an 8 by 8 chessboard, we want to define our domain. Our domain would include looping over all 64 spots on the board such that the constraints of the problem are met. You would do so by taking it row by row or column by column, and then you would evaluate each subproblem and decision-making points to navigate to the final solution. Next slide. Now we want to arrange the queens such that no two of the queens can attack each other, and no two queens are on the same row or column. So you want to recall that a queen can move any amount of spaces in each of the 8 possible directions of movement. We also obviously want to avoid an out of bounds error or placement of a queen. So all of these conditions serve as our constraints. Next slide. So now step 3, we want to determine the goals of our problems or subproblems. So the goal of the 8 queens problem is to place obviously 8 queens on the board, taking account the constraints. So each of the 64 decision-making spots would be a subproblem of our main problem. We need to determine what happens in each spot of the board where we have a possibility of a queen sharing the same row, column, or diagonal as another queen. So we want to outline the solution with respect to these constraints. Next slide. Now you can create a recursive solution to outline the subproblem, and the recursive solution will solve the subproblems in order to move towards solving the main problem. This is done by relating the main goal of the subproblem using the domain of choices and whatever constraints you set for the subproblem. The solution will keep solving until there are no more subproblems left and the goal is reached. Next slide. So here we have an outline of how a backtracking problem would ideally be outlined and constructed. So as you can see, our base case handles what happens when our problem's goal is reached. We then exit our loop, or we then loop through our domain and create a form of validating choices with respect to our constraints. After that, we recurse through the further states that the problem makes explicit. Next slide. All right, so here we have a practice problem for everyone to try out. In this problem, we have a situation where we're given an array storing a number where each element corresponds to a digit of that number. We want to avoid instances where the adjacent element has a digit of that number that differs by less than 2. So if we had an instance of the array storing a number like 563, we want to avoid printing 6. So we would end up printing the number 53 at the end. The problem also states to avoid instances where 0 is the first element of the array or the most significant digit. So go ahead and fill in the blanks of the solution with the proper code and think about how the general 4 guidelines I've outlined can help you solve the problem. Once you're finished, if you want, you can play hangman with us by clicking the link in the chat to open up a poll, or you can just vote your letter in the comments as we've established. All right, everyone. So it has been 10 minutes, so we'll go ahead and discuss the solution to this problem. So we're looking to print out all the integers, so where the distance or absolute value between them is greater than or equal to 2. And we don't allow digits like, for example, the digits in the number 98 or 97, since those two adjacent 98 and 97 digits, they do differ by less than or equal to 2. Um, so it's like a permutation, except we're storing the digits of the number in a number array. So then the print wrapper function dynamically allocates the array of size n, calls a recursive function, and frees the array. The print function at the bottom just prints out all the digits. Each digit in the array is stored as an array, and the array is stored as an array of digits. The integer k represents how many slots have been filled in the array, and the integer n represents the size of the array. Now, if k equals n, we're just going to call the print function by passing in the number array and its size, and then return, because we don't want to do anything else past that. Now we see the variable start being initialized to 0. Start represents the smallest valid digit for filling in slot k. So normally we can put a 0 for a digit, but we can't make 0 to the first digit. So to handle that, we just make start. We just set start to 1 instead. Now we loop through all the valid digits of a number, so like 0 through 9, and we reach a condition within that loop, which executes a continue command. We want to continue if the number we are currently trying to fill in for slot k does not fit the description of a unique integer. And the problem, recall that a unique integer is not unique if the number we're currently trying to fill in has a distance less than 2 away from the previous number. In our case, the current number is I, and the previous number is k minus the index of k minus 1 in the number array. So we need to take the absolute value of our previous integer minus our current integer to avoid negative values, because we're trying to find the distance between a number. And then therefore we cannot have a negative distance. We also need the condition k is greater than 0 to avoid any array out of bounds errors. Otherwise, if we don't enter that if statement, that means we have a digit that fits the description of a unique integer. So we use digit I in slot k and recurse through the remaining elements of the number array. And so that is a solution to our practice problem. I will now switch it back, or I'll switch it to Hannah for the recursive coding section.
Perfect. Okay. So now let's go. Thanks, Tequila. Let's go over recursion. And again, remember to post any questions that you have in the chat. So here are some tips and tricks which help me with recursion problems. So first off, solutions to recursion problems are by design usually fairly short. So if your solution is getting really long, you might be overcomplicating the problem. So watch out for that. Next, if you're struggling a lot with thinking in a recursive way and finding recursive solutions, try developing recursive solutions for problems which you have previously solved iteratively without recursion. So this will get you in a recursive mindset using easy problems that you really already understand. Next, a really helpful tip, just like backtracking, you want to practice some popular problems. These can include problems such as Towers of Hanoi, Fibonacci, factorial, flood fill, and many more. Lastly, keep in mind a basic structure of recursive functions. So in general, we have two segments, a base case, which is the stopping point for our function. And without a base case, we can get stuck in an infinite loop. So make sure we have it. And our recursive case, where you are usually manipulating the input in some way and then passing it to your function again. So here's a little visual, an example of thinking recursively. So this is the strategy for processing nested dolls. So you're going to initiate your function open all dolls. So if there's only one doll, you're in the middle, the innermost doll, then you're done. So you get to play with the doll. But if not, you have more dolls around your innermost doll. So you're going to open the outer doll and then process the inner nest in the same way. Cool. So now that we've run through some tips and tricks, let's talk about some common steps to approaching solving recursive functions. So after we go through a summary of solving steps right now, we'll go through a problem walkthrough so that you can get a taste of what it looks like to put these solving steps into practice. So first, you're going to find your base case or stopping point. And you can build your base case or stopping point off of input where you can return the value directly. And this is the simplest version of your problem. So next, you're going to work on your recursive section. You're going to redefine your problem in terms of simpler subproblems. And lastly, you want to formalize your subproblem into an algorithm. Yeah, so now let's use our steps on a problem. And the problem we'll be going over today is how to find the factorial of an integer. So the visual on the right gives a bit of an explanation of what this means. So let's talk through that first. So a factorial is the product of a number times all values less than it down to 1. For example, the factorial of 4 is 4 times 3 times 2 times 1, or 24. So to create a recursive function which outputs the factorial of a value, first we'll find our base condition. So to find our base condition, we need to think about all the values of factorial, which we immediately know the answer. So for factorials, that's 2 values. For an input of 1, we know that the factorial of 1 is 1. And we also immediately know that the factorial of 0 is 1. So our base case is n less than or equal to 1. And when we hit n less than or equal to 1, we know we can immediately return 1. Yeah. So next, now that we have our base case sorted out, let's work on a recursive section. To do this, we're going to try to redefine our problem as simpler subproblems until we spot a pattern that shows how these are connected. And so let's do this by working through a factorial example manually. So I chose to look at the factorial of 4, which we now know is 4 times 3 times 2 times 1, or 24. So within this, can we spot any subproblems? Well, within it, I immediately see the factorial of 3, which is 3 times 2 times 1. So our problem redefined tells us that the factorial of 4 is equal to 4 times the factorial of 3. So next, we want to do the same thing with the subproblem we found. So factorial of 3 is 3 times 2 times 1. So what subproblems are there? Well, I again see the factorial of 2, or 2 times 1. So just as we redefined our main problem, we now redefine our subproblem. So factorial of 3 is 3 times factorial of 2. And we're going to do this once more, this time with the factorial of 2. So the factorial of 2 is 2 times 1. And within it, I see the factorial of 1, which is simply 1. And we fit a base case here. So factorial of 2 is 2 times the factorial of 1. And just a reminder, so we don't need to continue this process each time until we hit a base case, but only until we see a pattern in how our problems and subproblems are solved. So let's formalize what we found as our recursive case. So for our problem and each of our subproblems, the factorial of our number was equal to itself times the factorial of the number 1 less than that. So here is our whole function written out in code with our base case and the recursive case we just developed, which is the returning n times factorial of n minus 1. Yeah. So now that we have some idea of how to approach these problems and some steps of it, and we've seen it in practice, it's time for you guys to try one. So in this problem, we're given an integer array with the top and bottom indexes given by high and low. And we're asked to return a sum of all the even integers in the array. So try to resolve this problem in a recursive way, perhaps using the high and low to your advantage. And we'll give 10 minutes of solving time. So once you've found a solution, playing hangman with us, and comment in the chat for the next letter. And again, feel free to pop any questions that you see as you're going through, or questions about what I just said, in the chat so we can get those answered for you. So it looks like our solving time is up, so we'll have to hopefully save our hangman in the last 5 most commonly missed types. So let's go over the solution to this problem. Yeah. So first, we see the base case given for our problem. So during our problem, we're traversing the array one by one, tracking our progress and our current integer index by incrementing low each time we process a value in the array. So how do we know when we process the entire array? So when low has passed high, high stays at the end value of the array consistently so that we know when we've processed all the values when we processed high too, shown by low being greater than high. So in our base case, we return 0 when we process the whole array, adding 0 to our sum because we've processed all of the integers. Yeah, so next let's talk about the recursive portion of our solution. So the first part we see is the section before our return statement. So this section is performing some intermediary processing. Since we only want to add even values to our sum, this section is checking if the current integer we're looking at, marked by low, is even. So if it is even, we collect its value in res to add to our sum. And if it's not even, we don't want to add it, so we leave res set to 0 instead. And next, we have our return call. So we add our current value or 0 to the rest of the sum being calculated by calling sum even again, but making sure to increment low by 1 so that we process the next integer in the array. So we're essentially creating the sum of our array here by saying the sum of an array is equal to its first value, which is stored in res, plus the sum of the rest of the array, or our array starting at our second value. Awesome. So remember to post any questions you have in the chat, and we'll move on to our next and final most commonly missed problem type, algorithm analysis, presented by Harrison.
All right, thanks, Hannah. And yes, the last but not least, algorithm analysis. And tips and tricks for this type of problem, I would recommend creating flashcards to help remember big O runtimes for common algorithms, along with anything else you might have trouble remembering, such as formulas, combinations, or permutations. And be sure to practice everything you do on paper to simulate the real exam as closely as possible. This will definitely help you with muscle memory and just not running into any unexpected things while you're taking the exam. And understand why certain algorithms have certain big O runtimes, because you may have to work with manipulating or altering them and actually understanding why they have what values that they do will definitely give you the edge that you need to pass. Now, also, you have to understand how to derive runtime from code, and studying the sorts will definitely help with this because it'll help you relate to how code relates to runtimes. And if you memorize the common sorts out there and their runtimes and why they are that way, then you can use those concepts that you know and use that to figure out runtimes of different code that you may encounter on the exam. And understand what runtimes are relatively faster than others. And to help with that, I included a little chart here in the slide you can see, and it shows the big O runtimes and how they compare to each other. Next slide, please. Now we're going to go over common steps to approach algorithm analysis problems. Now, a general outline of how we solve algorithm analysis problems that relate to finding the runtime of a function goes as such. Let T of n represent the runtime of a single query, and use the provided big O time and set up an equation to find the value of your constant. Solve for your desired value using the Tn equation, and then convert to the correct units if necessary. And you'll see how all of this fits together later. Next slide, please. So using what we had outlined before, here's a sample walkthrough of what we have. So you set T of n to the runtime of the query itself, and that's always given in the question. As you can see, the sorting algorithm takes big O n times the square root of n time to run. So you'd set Tn equal to that and put the constant c multiplied to it, and that's what you're going to find in this next step. Next slide, please. So you have 1000 values, which is given in the equation, and you equate that to n. And once you substitute that into the equation you've written out in step 1, you can have that second bullet point equation right there. T of 1000 equals C 1000 times the square root of 1000. And once you solve all of that, you get 0.2 milliseconds. Now, this is very important because you want to make sure you memorize what units you're using and how to convert that, because you see in the question itself, it says the algorithm took 0.2 milliseconds, but the answer that it wants is how many seconds. So keep that in the back of your mind. At the end, we're going to convert that to seconds later. But as a result of solving for C, you see you have 0.2 over 1000 times the square root of 1000, and you're going to use that constant you found right there in your next step. Next slide, please. Okay, so like the first equation, it's T of n equals to C times n times the square root of n. Except this time, instead of substituting 1000 in, you substitute 900,000, because that's the size of the array you're solving for, and in this case, that would be your n. So you substitute 900,000 for all the n's, but for the C value, you use the constant that you found in the second step. That constant, of course, is 0.2 over 1000 times the power of 1000. And in basic algebra and arithmetic, you eventually come out with 5,400 milliseconds. Now, pay attention to the unit there. That's given in milliseconds, and then you want to convert that to seconds. You're going to have to memorize this part. Milliseconds is 1,000ths of a second. And then you just move the decimal point over 1, 2, 3, and you get 5.4 seconds. All right. So now it's time for you to take a shot at this. And we have the practice problem up on the slides. If you finish early or you would not like to do the question, then feel free to play hangman with us. And we'll have 10 minutes set aside to do the practice problem. Hey there, Socket. I just read your question, and I think we are not provided calculators. So all that math you'll have to do by hand. So that's why it definitely helps to practice anything you do on paper and pencil. Yeah, I feel that. Hey guys, so we'll be wrapping up soon, and we hope you enjoyed your time here. So if you have a minute to spare or anything, please let us know how we did. And we have a link in the chat that links to a feedback form, and we'd appreciate if you guys could fill that out. All right, and with that, that's our 10 minutes for solving the practice problem. And now we'll go over the solution. So to approach this problem, there are definitely many ways to do this, but the solution that the foundation exam had set forth is this. You want to equate both of the runtimes, or put both the runtimes on one side of an equation and both of the given times on the other side. So you can see that one is 20 milliseconds and the other one is 10 milliseconds. So if you make an equation and kind of compare them to each other like this, then you can just solve for the unknown variable. In this case, the c's cancel out. You don't have to find the constant. And you're just left with log n over 4 log 10 equals 2. And then using that, you do basic algebra and solve for n. So in this case, you would multiply both sides by 4 log 10, the 2 multiplied by the 4, which is the constant in front. You get log n equals 8 log 10. And for this next step, you have to know a little bit about algebra or arithmetic involving logs. The constant on the outside of the log moves into the log itself and becomes 10 to the power of 8, which is the constant outside. And since you have a log of both sides, log n equals log 10 to the power of 8, you can drop both logs, and that will be 10 to the power of 8. I know in this solution they didn't really give the units, but keeping track of it the entire time, you know that's n equals 10 to the power of 8 milliseconds. And let me see, in the problem, it asks, oh, actually, no, milliseconds, my bad. That's canceled out in the beginning. This asks about users. So, my bad. The answer here would be 10 to the power of 8 users. All right, thank you.
Awesome. Thank you to all of the presenters. So with that topic covered, we'll be wrapping up our event today. First, I want to send a massive shout out to the amazing team who helps put on this event, put it together, and check out our Instagram at DCSUCF to hear more about the incredible 2020 and 2021 team. There'll be posts about them soon. Next, if you'd like to stay updated on our future events and more things like this, follow the link on screen to our website where you can join our group, see more info about core team applications, and follow our socials. And we'll be sending out an email soon with the feedback form, which is in the description, so fill it up, and a link to our resource sheet, which goes even more in depth on the material you've seen today, plus some other quick guides for more foundation exam topics. So thank you all for attending and getting your study on with us, and we wish you luck in the upcoming exam. As I mentioned, we're going to do one quick hangman round so we can get him through this last one. So pop everything you have into that those comments. Let me open up the comment view. Cool. Yeah, so let's see if we can get him through this one last word, and then that'll be our wrap up for the end of today. Do you have any guesses? I'm going to start with an A. Oh, perfect, an A. Okay. We'll see how fast we can get through this one. E, okay. Good guesses so far. And while this is up on screen, make sure to follow that QR code and link. M, okay. Oh no. Okay. Okay, we have, oh, S is already in there. Can't choose that. R, okay. Almost there. H, okay. Have, oh. Accurate, okay. Oh, well, we did have a C, so we're almost there. Let's see if we can get through this one. N. I think I have a guess if anyone else can solve it. Think of Alaska. Oh, okay. One letter away. Anyone have a solution? Anchorage. Awesome. Cool. Good job, guys. Thank you for joining us today. And fill out that feedback form in the description so we can continue putting on events for you guys and make events like this even better for you guys. Thank you so much, and thank you to my entire team. Have a great day. Bye-bye.